Hello, am I audible?
Yes, sir.
Okay, so then we can begin. Uh, Welcome to the fourth problem solving session of the course Design of Power Electronic Converters. The course is being taught by Professor Shabarinath, and my name is Soleh Khan, and I'm a PhD student at IIT Delhi, and I will be conducting this course, the problem solving session for this course. So we'll again begin with a summary of what was taught in the fourth week, and then we'll do some problems regarding the content of this week. And just to pick up from one topic that was left in the last week, DSAT protection, which I could not cover, so I'll start with there. And then we'll talk about bootstrapping and some other K-driver related issues. And finally, the main topic for this week was Snubbers, introduction to Snubbers, and RC and RCD Snubbers. So DSAT protection is a type of overcurrent protection, and DSAT is short for desaturation. And what is desaturation? So, for example, if we have an IGBT, which is shown here, and these are the output characteristics of the IGBT. And in power electronics, we know that we operate the switching devices in either on or off. So for the IGBT, it would be either forward blocking or the cutoff region, or it would be in the saturation region. And we know in the saturation region, uh, the voltage drop is very less compared to the the full blocking voltage. But what happens in the case of very high currents, that happens in case of like a fault or some short circuit, if we are if we have a particular VGS for a particular VGE, as the current increases, the voltage drop across the uh, across the device, the VCE drop, it also increases. And in fact, it goes from the saturation region to the active region. So for example, here I've shown if green, the point is what is the normal current, and due to some reason, uh, the current goes high due to a short circuit or a fault condition. So the current will follow, it will follow this curve because we have a particular VGS or VGE. So it will follow this curve and it will go from saturation region to the active region. So that is why it is called desaturation. And what happens here is that the voltage drop, forward voltage drop VCE, it also increases substantially. So we can use this fact that the voltage drop increases as the current goes very high. We can use this fact to detect uh, whether we are in a short circuit or fault condition. So that is what is done in DSAT protection. We monitor the VCE voltage when the device is on, and if it crosses a certain value, then we understand that a fault has occurred. So we will uh, do the necessary measures to stop the fault or avoid damaging the switch, whether we can turn off the switch or uh, turn off some other aspects, some input voltage or something else. But mainly, we're using DSAT protection. When this threshold is reached, we will turn off the gate pulses to the device so that the switch becomes off, and usually the short circuit is avoided. And there are many different ways how this is implemented in practice. And in the course, one particular way was shown, and I can here show another way, which is used in this gate driver IC from Texas Instruments UCC 21750. And in this, what is done is that uh, the gate driver has different pins, and it has one pin called the reset pin. And this pin has to be connected to the drain or collector of the device. And it has to be connected via a high voltage diode so that uh, in during the off condition, when the device is off, then there will be a very large voltage at the collector point. So in that case, uh, it should not damage the IC. So that is why we have a very high voltage diode here that will block that during that condition. But when the device is on, then the voltage drop across the device will be very less. So in that case, the diode will be actually forward biased, and there will be a current that can be pushed through the Desat pin. And so in this particular IC, what is done is they have a constant current source here. And inside the IC, they have a threshold. For example, here it is, a threshold is equal to 9 volts. So when the voltage at the Desat pin becomes 9 volt, at that time uh, a fault condition will be triggered, and the gate driver will turn off the pulses to the device. So how is this? How will the Desat pin reach 9 volt? So the way it is done is we have a current source here which provides a constant current. Usually it is very small in microamperes, hundreds of microamperes. So this current is constantly pushed when the uh, gate pulse is high to the device. And in that case, what will happen if the voltage at the collector terminal is low? That means we're not in a fault condition. The current will, so the voltage here will be, let's say, 2 volts. And then the diode will have some drop, and then this resistor will have some drop based on this current, the microampere current. So then we will get some voltage here which will be less than 9 volt. But when during a short circuit or fault condition, when the current goes high, then this voltage will become higher, and it will as it goes high, the voltage here also becomes high, and once it crosses the 9 volt threshold, then the fault will be triggered. And there is something called this blanking capacitor which is also provided, and it is important because uh, when the gate pulse to the driver will be high, so it will start the Desat protection. However, it will take some time for the device to turn on, so it will take some time for the voltage across the device to drop. So during that time, if there is uh, if there is no capacitor, and instantly the voltage that is at the collector terminal, it comes at the Desat pin, then the fault will be triggered, even though there is no fault condition. It is just the device was off, so it had a large voltage across at the collector point. So, and when we turn on, it will take some time to for that voltage to drop. So, in order to uh, uh, avoid fault detection during the turn on of the device, we have this capacitor, and this capacitor will actually take some time for the voltage across it to increase. And the capacitor value is chosen in such a way that it will take enough time for this capacitor to charge, that is more than the turn on time of the device. So this is just a summary. If you want to go into more details, then there are some application notes and the gate driver data sheets. They actually provide more information here. But the point is just to monitor the collector voltage, and in case of a fault, the collector voltage increases, and then we detect that a fault has occurred, or a short circuit or a high current condition has occurred. So this was about DSAT. Next, we have the bootstrap capacitor based gate drivers. And so the first condition is question is, why do we use bootstrap? So we have previously seen that in case of a half bridge configuration, the voltage of the switching node, which is the midpoint between the two switches, is not a constant voltage, but it is a switching voltage, and it varies between 0 and the DC bus voltage, the VDC voltage, which can be very high. So the high side gate driver, it requires a gate voltage supply which is referenced to its source or the emitter, which in this case is a switching voltage. So we saw previously in the last week's lectures that this can be done using an isolated DC to DC converter. However, the problem with that is that it is quite expensive. To The DC-DC converter is the small DC-DC converter is a very expensive component. And if we have like many half bridges, like a three-phase converter or a multi-level converter, then we will require many of these uh, isolated DC-DC converters. So that is why we have another option, which is called bootstrapping, or using a bootstrap capacitor gate driver. And in this case, we just have a additional capacitor and diode in the circuit without any need for uh, another DC-DC converter, isolated DC-DC converter. So it's an inexpensive alternative for high side gate driving. And in a summary, how it works is we have a voltage supply. Yeah, the capacitor charging path, it will be explained in this figure basically. So, the way it works is, first of all, the low side switch has to turn on. So uh, for the bootstrapping operation, you have to make sure that the first switch to turn on would be the low side switch. And when S2 is on, so at point A, you get 0 volt. So it is the point A is connected to the ground, right? And now we have the low side gate driver circuitry, and we have a voltage source connected to it, which will be the 15-volt voltage source. And you see, if you see this loop, when S2 is on, then the point uh, A will be at 0 volt or ground potential. So, and if we assume that C bootstrap, this capacitor is discharged initially, then basically this point, the diode point, will also be at ground potential. And on the cathode side of the diode, we have 15 volt. So that is why the bootstrap diode will be forward biased. So during the time when S2 is on, the diode will be forward biased, and the bootstrap will get charged. And if the on duration of S2 is high enough, this length of time is uh, enough in the length of time is large enough that C bootstrap will get charged to the full VG voltage. So let's say 15 volt. And then in the next case, when S2 becomes off, so when the high side circuitry, we turn it on so that S2 becomes off and S1 becomes on. So in that case, the potential of point A will be VDC, which means that this diode will be reverse biased. So in that case, now this the voltage that is across C bootstrap, this voltage which was initially charged to VG, this will be used to drive S1. So this is basically the principle of how the bootstrap operation works. So in the condition when the low side switch is on, our bootstrap capacitor gets charged, the diode is forward biased, and bootstrap capacitor gets charged to the gate voltage. And then in the next uh, interval where the high side switch is on and low side is off, and then the bootstrap diode gets reverse biased, and the capacitor provides the voltage for the high side device to turn on. So I hope that is clear, the path of the charging. And the discharging path will basically be through the high side circuitry. It will go to the gate, and there'll be all the resistance, gate resistance, and everything will be here. And just like Desat, there are multiple implementations of this kind of a circuit, and one implementation was shown in the main course. and but I will not go into that here, and just the concept I wanted to explain. Bootstrap, it you can it it can be available at discrete components. It is also available as ICs, and usually in that case, what is done is that this whole thing, the high side circuitry and low side circuitry, is in one IC, but the capacitor and the diode, that you have to choose. That is that those are external components that you have to choose depending on uh, your rating of your converter, your switching frequency, and all these things. So it can be available as IC or discrete components. There are different options available. Now, there are some limitations for this, and one limitation is that it does not provide the isolation that is provided by the DC-DC isolated converter that we saw previously. This circuit, as you can see, there is no isolation. This it is just direct connection. So that can lead to low noise immunity, because any noise that is in the high power side, so the device, so this is the power side of the circuit, any noise that comes in, it can just travel to the gate driver side, and that can cause problems, that can cause false turn-ons or turn-off. So it will lead to low noise immunity. And secondly, it can only be used for half bridge based circuits. So as we saw, we require there is a condition that S2 first has to turn on so that we get a path for the bootstrap capacitor to get charged, and then in the next interval only then we will discharge, and so this will happen again and again. So when S1 is on and then we turn it off again, the bootstrap capacitor will get charged. So that is why we have to have this kind of a configuration. So it need not be, S2 need not be an active switch, it can also be a diode. In that case, the current path will be through the load, the inductor, or just like in a buck converter. But the point is, it has to be a half bridge or a leg based circuit where we have one switch and another switch in the same leg, switch or diode. So that is one limitation of this circuit. However, it is mostly these kinds of circuits are in most converters. Like if you have a buck converter, boost converter, buck boost converter, all of these have uh, half bridge or leg based circuits. Similarly, H bridge, single phase or three phase VSI, all these have actually half bridge circuits. So it can be used in all these circuits. Another limitation is that it can be used for low gate currents and low switching frequencies. So, so this is because of the limitation of the capacitor itself. So if we want to, for example, if we have a device that requires very high gate current, then if we have a very small bootstrap capacitor, then it will get discharged while it supplies that current. So it will not be able to supply the 15 volt for the entire duration of the on time if the current required is high. So one solution you can think of is that we will just increase the value of this capacitance so that it can then provide more current without discharging. But if the capacitance value increases, then it will take more time for the capacitor to charge as well. And we saw that the only time for the capacitor to charge is when the S2 switch is on. So it depends on the switching frequency of the circuit. If the switching frequency is high, then the time duration where the low side switch is on will be very small. And if the capacitance, bootstrap capacitance value is high, then it may not get enough time to get charged to the full VG value. So that is why there is some limitation on the switching frequency and the current that it can supply. And in those cases, we have to use some other uh, gate driving circuitry like the isolated DC-DC converter that we saw. So that was about the bootstrapping gate driving method. So next we can just quickly talk about some other gate driver related aspects. One is pulse transformer based gate drivers. So here, instead of using an optocoupler to uh, isolate between the controller output PWM and the gate supply, we can use a transformer, a very small transformer. And the reason it's called a pulse transformer is because the input and output of this transformer are pulsed PWM signals. And one advantage here is that it can both supply uh, the PWM signal as well as the power of for the gate driving, uh, the voltage, the high voltage, as well as the uh, isolation for the signal. So basically, signal and power it can both supply in the same circuit. But there are some problems associated with it. One is that it can only transfer the AC component. So if you want to transfer the DC component, you require some other capacitors and diodes, so which are shown here. And then it also has its own parasitic components. And if the switching frequency is high, then it causes some problems in that case. So next, we also want there is also parasitic components in the gate path. So first of all, we know that, for example, if we have a MOSFET or an IGBT, we know there are parasitic capacitances that are shown here. Yeah, in addition to these parasitic capacitances, we will also have parasitic inductances. So, for example, between the leads of the device, the discrete device, and also on the path of the PCB. So there will be some inductance as well here. And then we have the RG resistance that we put externally. So this forms a RLC circuit. So it will lead to some spikes in the voltage that actually comes across the G and S. And if the spike is too high, then it can actually damage the device. And if the spike actually goes below the threshold or below the miller, so it will actually create some problem during the turn on and turn off. So this is also an important aspect that needs to be considered. So that is why what is done usually is that the gate driver is put as close as possible to the device so that this inductance is limited, the parasitic inductance. Next, we also have some speed enhancement circuits. So basically, just like we saw that there's an it's an the gate drive circuit is an RLC circuit, or if we ignore the L, it is at least an RC circuit. And depending on the value of R, the RC time constant will change. If the value of R is very high, then it will take a lot of time for the gate voltage at the actual device to get charged. So based on this RG value, we can actually change how fast and how slow the device turns on and turn off. And usually what we want to do is we want to reduce the turn off time. The turn on time is limited by the reverse recovery of the other device in the circuit. For example, there will be another diode in the circuit, or even if there is another switch in the circuit, there will be deadband between the switches and the diode will get involved. So that is why RG on is usually uh, we have to give some time. It is limited by that diode reverse recovery. But RG off, usually we try to make it as small as possible so that the off time is reduced. And this can be done in many ways. One of the ways is shown here. We have, because during the off time, the uh, the gate to source has to be discharged. So the current will be from the device to the source. So if we have this kind of a circuit where we have a diode in parallel with another resistance, or it can even be a short circuit. So in that case, when the device turns off, the negative current will actually go through this parallel path, and it can have a lower resistance so that it will actually uh, the device will get discharged quicker. the CGS will get discharged quickly so that it will turn off quickly. And so in modern gate drivers, they actually have different output pins. So one is the for turn on output pin and another is for turn off. So this thing is actually internally in the gate driver IC, and you just have to provide different resistances in the different pins of the gate driver. So, so this was all about the gate driver aspect. So next we have to come to the snubbers. So in introduction of snubbers, the question is why do we need snubbers? So what is the problem that we want to solve by using snubbers? So before this, we have been considering somewhat ideal circuits. So in a half bridge, we consider there will be two devices and a DC source. But in actual practical cases, there will be some other parasitic components. So because any wire that you have, it will have its own resistance, it will have its own inductance. It will be very small, but it will have some small value of resistance and inductance. Similarly, between any two conductors, you will have some capacitance. So, so that is what is shown here. So there is a parasitic inductance. So actually, in practical cases, the parasitic inductance will be between any 2 points. So for example, from the VDC positive to the device, there will be inductance, and from the between the two devices, there will be inductance, and then from the VDC minus to the other device, there will be some parasitic inductance. And I've lumped all those parasitic inductances here as one LP inductance. Similarly, there will be RP parasitic resistance. And we know that the devices they have parasitic capacitance CDS across the drain and source. So so these will actually form an RLC circuit. And because the value of this RP is actually very small, this kind of a circuit will be usually an underdamped circuit. So what is the problem that we have with this kind of a situation? So what this leads to is when the device turns on and off. So for example, here I've shown the condition where the device is turning off. The voltage across the device should have just gone up and then reached the VDC value and then stayed at that value. But in practice, due to this RLC circuit, what will happen is that there will be ringing and voltage spikes. And mainly during the turn on, because of the reverse recovery, it will create more issues. So in that case, there will be voltage spike, and the voltage spike it can damage the device because the device will have a voltage rating, and the if the spike crosses that voltage rating, the breakdown voltage rating, then it will damage the device. Similarly, the device will have a DVDT rating, and if the DVDT rating gets crossed, then it will also can also damage the device. It can also, if the spike is too high, it can generate sparks. It can maybe cross some isolation boundaries. It can create some other issues. So that is why we want to limit the voltage spike, and we also want to limit the DVDT. So there is a question in the chat that is the parasitic inductance because of connecting wires? Uh, yes, basically the connections between the different terminals, whether it be wires or whether it be the PCB copper traces, whether it be actual the device. So if we have a MOSFET, it will have its legs, the three metallic legs of the MOSFET. So all these things contribute to the parasitic inductance, whether it is the PCB trace that is basically this trace, whether it because for the device there is the semiconductor inside the the discrete device, and then there will be metallic legs that come out of the device. These metallic legs will also have inductance associated with them, and then they will be connected on a PCB or some other kind of a board, and between the two devices there will be some PCB trace that will also have its inductance. So all these things contribute to the inductance, and all these things will also have their own resistances. And the capacitance mainly is the device capacitance, which will be contributing to this phenomenon. So basically, the problem that we're facing is due to these parasitics and uh, when the device turns on and off, and mainly during the turn off, there are some spikes in the voltage that can cause problems. So we want to limit those spikes. And for that, we use snubbers. And there are many kinds of snubbers. And what we basically saw in the course were only two RC and RCD snubbers. And for example, here I'm showing an RC snubber, which basically is a resistance and a capacitance in series with a capacitance. And the whole thing is connected in parallel to the device whose voltage we want to limit. And what this does is it changes the RLC circuit parameters. And since these RS and CS is within our control, the values of these RC and RS and CS is within our control, we can actually change how the RLC circuit behaves. So we can slow it down, we can reduce the spike and all these things, as we'll see. And so what will happen is that we can actually change uh, the DVDT, we can change the peak value of the voltage. So all these things can be done using these snubbers. And so what are the advantages or uses of these snubbers? So we can reduce the voltage spike, we can limit the DVDT or DIDT as well, and also we can transfer the power dissipation from the switch to the resistor. So because there is another path now that comes in, and some of the switching current will actually go through this path. So some of the switching loss that took place in the the device now can happen in the resistor. So so it may not necessarily reduce the switching loss, but it can distribute it so that the device temperature may be less, and in that case the resistance will get loss, and so basically it can distribute the loss in different components. But not only the distribution of loss, but it may also be possible to reduce the overall losses. And there are different methods to how to do that. And finally, the EMI can also be reduced because the EMI is related to the DVDT and DIDT. And if we can control and limit the DVDT and DIDT, we can actually control and limit the EMI as well, which I think we'll take on later in the course. So now uh, RC snubber analysis. And so this was taught in the course, and it was there's a lot of derivation that I cannot go into right now. I'll just briefly summarize how it was done, the basic principles, and then we'll go to the problem solving. So this is the circuit that we are considering right now. So we have the device here, which in this case is a diode, and across this device we have the RC snubber, and then we have this the parasitic inductance. So the E voltage is basically the turn off voltage, the full turn off voltage that should come, that will be blocked by the device. And this small E voltage is the actual instantaneous voltage that is blocked by the device, and ID is the device current, and I is the snubber current. So what happens is that as the device turns off, the current through the device reduces, and then it will uh, change direction and it will reach a reverse recovery peak. So as you see, the direction of the current is taken as opposite to the device current, and once it the basically the device gets turns off, so it will start blocking the voltage, and then the current will actually transfer to the snubber. So this IRR will actually transfer to the snubber, and then there will come some voltage across the device. So the blue current is the device current, and then at a certain point, the device starts blocking the voltage, and the current goes through the snubber, and the snubber current will start from IRR, and the voltage across the device, it will start from, first of all, there will be the CS capacitor will be discharged, so the IRR current will flow through the resistors, so there will be some voltage drop, and that is what will come across the device, and thereafter the device voltage will start to increase, and the capacitor CS voltage will also start to increase. So now what we want to do is we want to find out this E1 value as well as the time T1, and then we want to see how they relate to RS and CS, and then we can change the value of RS and CS and change E1 and T1. So the way it is done is we first find the KVL equations here. So this is the first equation, that it's a KVL equation of the snubber and the parasitic inductance loop, this loop. And based on this equation, we can actually find a differential equation that is shown here by differentiating it. And we also have another KVL equation, which is the device equation using the device and the parasitic inductance, this KVL. And this will give us the device voltage across the device, instantaneous voltage across the device. The initial conditions we have is that the capacitor is discharged. So we are sort of ignoring the voltage drop during the on time of the diode. And so we are assuming that the capacitor is discharged. We are assuming that when the snubber starts conducting, the initial current is IRR, and the initial voltage across the device in that case will be RS times IRR. So basically this current or this voltage. So based on these uh, differential equations and the initial conditions, then we can basically uh, solve this circuit. So what we do is we solve the differential equation for IT, the first differential equation for different cases. So it can be underdamped, overdamped, or critically damped. And we use the initial conditions to solve for IT. Then once we have solved IT, we can find the the IT is the snubber current, and then we can use the snubber current to find the device instantaneous voltage. So in this equation, if we have IT, we can find didt, and then we can, in this equation, we can find the instantaneous voltage across the device E. And then we can find the time t1 at which E is maximum by setting dEdt equal to 0. So when we set dEdt equal to 0, then we will solve that expression to get the value of t1, which is the time at which E is maximum. And then once we have t1, we can uh, substitute it in the equation for E to find E1. And then finally, we want to find E1 by E, which is the normalized value of the voltage spike. So if we have the voltage blocking E, we want to find E1 by E. That means how much uh, the spike is higher than the actual uh, blocking voltage. For example, if the blocking voltage is 100 volt and the spike is 150 volt, then E1 by E will be 1.5. So 1.5 times the blocking voltage, that is our uh, peak uh, spike. And then we also want to find the dVdt average, which in this case we are defining as E1 by T1. So basically the peak voltage divided by this T1 time that we are determining, labeling as dVdt average. So these two things we want to find out, and then we can see how we limit these two based on the values of R and CS. So for the solutions, we have to see some terms in the analysis. So the first term is the undamped natural frequency, which would be just 1 divided by the square root of LP times CS, the parasitic capacitance times, the parasitic inductance times the snubber capacitance. This will be the undamped natural frequency. Then we have a factor called alpha, a decrement factor. It is defined as RS divided by 2LP. And then the damping frequency will be omega d equal to the square root of omega 0 square minus alpha square. Next, we have the damping factor. So this will be how we determine the different cases. So if the damping factor is less than 1, then we have underdamped case. If it is greater than 1, then we have the case of overdamped. And if it is equal to 1, then we have critically damped condition. And this is how it is defined. And finally, we have what is called the initial current factor, chi. And it is given here the expression for chi. And what we'll actually do is we'll solve these different equations in terms of all these parameters that we have seen. And then finally, we'll determine a particular value of uh, damping factor zeta and the initial current factor chi. And then we'll use it to, once we know a particular value of this, we can find CS and RS based on these. And just to note that this chi factor is actually chi square is equal to the initial current energy in the inductance divided by the final energy in the capacitance. So these are the solutions as were shown in the course. Uh, for different values of the zeta, the damping factor, we have different expressions for E1 by E and the dVdt average. And these are very complicated expressions, and uh, you can use MATLAB to find them, or you can use the plots that we'll see to uh, design the snubbers. So the design is actually you have to choose whether you want to minimize the voltage spike, or you want to minimize the dVdt, or you want to use what is called a compromise design. So you want to where we minimize the product of the voltage spike and the dVdt average. So in that case, we will sort of reduce both the voltage spike as well as the dVdt, but it may not be the minimum of either one, but the minimum of the product. So for example, I will only show the first case. The other two are similar. So based on these solutions, what we can do is as the uh, as the damping ratio varies and the the initial current factor is varied, how does E1 by E change? So it is shown here one figure that as we can basically plot these equations that we saw for different values of chi and different values of the damping factor zeta. And in this case, we get a plot like this. And as you can see, for a particular value of zeta, the particular value of chi, as zeta increases, the peak voltage, the normalized peak voltage, it actually first reduces and then increases again. So there is actually a minimum point here. And similarly, for different values of chi, we can find different values of the minimum point. So what we can do then is we can plot these minimum value points uh, for, and we can see what the different values of chi and different values of zeta. For example, if the chi is 0.4, then the minimum value would be, let's say, 1.2 somewhere. So 0.2, 0.4, the minimum value is 1.2 somewhere. Similarly, we can plot all these different values like this in this figure. And in the same figure, we can also plot the value of uh, zeta for these minimum points. And then once we choose a particular value of E1 that we want to limit the voltage to, then we can find E1 by E in this graph. And for example, if the E1 by E is 2, that is E1 can be twice E, twice the value of E, then we can, based on this, we can find what is the value of the current factor, initial current factor, and what is the value of uh, uh, the, the damping ratio. So there are questions. So first question is, what can we measure the parasitic element values? We can, but it is not so simple. It is actually quite complicated to measure these values. Uh, Usually, so in these problems, in the questions and the course, you will be given the value itself. You will not be able to, uh, because these values are very small. So if you want to measure, you have to get a very accurate and very uh, precise measuring tool, which is very difficult to get. So the LCR meters or the impedance analyzers that we have, they cannot measure inductances, the parasitic inductances to this value. So what is the other option is you have to basically determine it using analytical methods that we can do it. So if you have a PCB, uh, what you can do is there are some softwares which actually it will give you the parasitic inductance based on the trace width, the copper width, and the length of the trace. All these things, if you give it to the software, it will actually provide you with the parasitic inductance. And for the device, it may be the case that the manufacturer of the device, it will give you how much is the parasitic inductance in the device. So there are a lot of things that comes into the parasitic element measurements, and but it's not so simple. But what you can do usually is you can have a guess of what the parasitic elements can be. So we can estimate that it cannot be very high. It cannot be in the millihenry range, for example. The parasitic inductance will not be in the millihenry range for a well-designed converter. And it will not be as small as it cannot be like a few picohenries. So usually is in the hundreds of picohenries to some tens of nanohenry, this range. And based on that, you can select a value and you can get an idea of the snubber values that you want to use. And as was mentioned in the course, this analysis that we are showing, it is not fully accurate because there are a lot of uh, assumptions that we are making to simplify this analysis. And that is why if you select a particular value of R and C for the snubber, you will not get exactly the value of E1 that you uh, get from the analysis. So it will be slightly different. So then you will have to actually change the value of the snubber resistance and capacitor to fine tune the uh, the overshoot that you get. So that will be on a trial and error basis at the end. So in the second graph, the y-axis. So the y-axis here is actually so these are dimensionless values because E1 by E is just a ratio. It does not have any unit. Similarly, the damping factor does not have any unit. So this is basically just values from 0.1 to 10, and they will apply to both E1 by E as well as to zeta. So in this case, the y-axis is for both E1 by E as well as zeta, as well as this third curve that is shown here. So basically what you will do is, if you want to minimize the voltage spike, you have a particular value of E1 that you want to limit your voltage spike to, then you can find E1 by E, And based on this graph, you can find the value of chi and zeta. And then once we have the values of chi and zeta, we can use these expressions to find CS and RS. So uh, this was basically the summary of the course. And lastly, I want to say that if you want more details, this the analysis that we showed for the RC Snubbers that was shown in the course, it was actually based on this academic paper. If you want more details, you can find it in this paper. So it was cited in the course lectures as well. So here I'm also citing it. So if you see this paper, all the details and some more discussion will also be provided there. Now, before we come to the problem solving, we'll just have a short break. So we can begin uh, at 4:05, I guess. Okay, so we'll have a short break and then we will come to the problem solving. So it will be a design of the RC snubbers based on some parameters that are given. Okay, we can continue then with the problem solving session. There's a question in the chat about Bootstrap ICs. So I've not actually worked with many Bootstrap ICs. I've more worked with the isolated DC-DC converter based ICs. But so I don't remember any Bootstrap IC part numbers. But if you email me, I will try to find out some part numbers and then I can uh, reply to you in the email. So the problem solving, we have a question that we have a buck converter using two MOSFETs. So it is what is called a synchronous buck converter. However, even though we have two MOSFETs, one MOSFET is used like a switch, the other MOSFET is used like a diode. So even though the circuit is a synchronous buck converter, it is operated like a normal buck converter. So only the body diode of the second MOSFET is used and no gate pulse is given. And the input voltage to the buck converter is 50 volt and the parasitic inductance is estimated as 8 nanohenry. So again, this is an estimation. Uh, it will be difficult to calculate or measure this value. So this is how the circuit is looks like. So we have these two MOSFETs, but the second one, we are only using the diode portion, the body diode portion. We are not using the device, the channel. So we'll not give any pulses to this MOSFET. And like you have to, even though it is not written which MOSFET we give the pulses and which MOSFET we use as a diode, but it is understood that it will be the low side device because the top one is the main controlled uh, MOSFET. If this one we use as a diode only, then the buck converter will not work as a buck converter. And across the low side device, the diode one, we will have the RS snubber, the RC snubber, and then we'll have to find out the values of all these things. So the first question regarding this setup is from the data sheet. So that is the data sheet of the MOSFET. The MOSFET part number is given. The DVDT limit for the body diode is obtained as what? So this is the question, and we have to give it in the units of volts per nanosecond. So if you go to the data sheet of the device, you will see that the peak diode recovery DVDT is 7 volts per nanosecond. So the answer to this problem is the first question is 7 volts per nanosecond. And then the second question is asking about using the typical values of QRR and TRR given in the data sheet. The reverse recovery current is calculated as, so if we again go to the data sheet in the diode parameters, we will find that it has given the diode current, the continuous and pulsed currents, the diode forward voltage, and the reverse recovery time and reverse recovery charge. And these are given for typical values and maximum values. And the question is asking about the typical values. So the datasheet gives us QRR and TRR, but as we saw for the RC snubber analysis, we require the value of IRR. So how will we get, we can use TRR and QRR, and if we just assume that uh, the diode current is like a triangular portion during this negative half, if we assume this to be a triangle, then the QRR will be half of the IRR times the TRR. And based on this expression, we can find the value of IRR. And we substitute the values of the typical QRR and TRR. And then we will get the reverse recovery current, which is 8.78 ampere in this case. So as you can see, it can be quite substantial. So the forward current was 16 ampere in this case, and the reverse current went to around more than half of this value. So that is why this reverse recovery is actually quite a significant uh, effect. So that is why we want to limit it and control it. So now the question is saying that we want to use an RC snubber across the body diode, and we want to limit the peak voltage and as well as the DVDT. So we want to limit the peak voltage to twice the input voltage, and the DVDT average, which would be basically E1 by T1, we want to limit it to half of the DVDT limit given in the data sheet for the body diode. So first we have to design this number by limiting the peak voltage. So in this question or in this these problems, we will do all three of these cases where we design this number by limiting the peak voltage. In the second case, we'll design it by limiting DVDT, and in the third case, we'll use the compromise design. So first, starting with the peak voltage, the value of E1 by E. Now this is quite simple. E1, as we saw, is twice E. So E1 by E will simply be 2. So in this case, E is 50 volt. So E1 will actually be 100 volts. So we want to limit the spike to less than 100 volts. So E1 by E is 2. And in the next question, now it is told that the corresponding values of chi 0 and zeta 0 are 2 and 0.4. And this actually you can see from the graph. So this graph is taken from the paper that I mentioned. And once we have selected E1 by E as 2, then we can find what is the value of chi and what is the value of zeta. So in this case, chi is around 2 and zeta is around zero point 0.4. So that is what is given in the question. It is just almost a rounding off. It is rounded to 2 and it is rounded to zero point 0.4. So in the next questions, we will use the chi value as 2 and the zeta value as zero point 0.4. So now we are told to find the value of Cs. And as we saw in the Cx expression, we only require uh, the parasitic values LP, IRR, and the values of chi and zeta. So in this case, we require IRR, LP, E value, and zeta. Okay, from so this slide. So basically, here once we know the value of E1, we can find E1 by E. So in this case, it comes across as 2. And once we have E1 by E, we can use this graph to find the corresponding values of chi and zeta. So this graph is for minimum E1, minimum voltage spike. So we saw that E1 by E is equal to 2 because we want to limit E1 to twice E. So from the y-axis, if we find the 2 value and we go to the E1 by E graph, and then we can go to the x-axis. So that will be the value of the corresponding value of chi, right? Where it intersects the x-axis. And this line will also intersect. So basically for this value of chi, the value of zeta will be, if we go up back to the curve for zeta, and then the value of zeta will be what is shown here around 0.4 or zero point 0.5. So this is how we use this graph to, yes, so it is, that is why this whole thing is given in normalized terms. So if E1 by E is given, so independent of what is the value of E, E can be 50 volt or 100 volt, but once we have the value of E1 divided by E, uh, we can use this graph to find these values. So for E1 by E or equal to 2, uh, this will be the value of uh, zeta and chi for all cases. So then we can use this expression to find CS, which in this case comes as 61.67 picofarad. So here be careful that you use the all the values in SI units. So LP is 8 nanohenry, so it will have a 10 raised to the power minus 9 uh, term attached to it. So then we can also find the value of RS using the expression that we saw previously. So again, so here we will use the value of CS that we found in the previous question, and zeta is as the question itself tells us it is zero point 0.4. So again, we'll use the value of LP and CS, and we'll just keep in mind the SI units, and RS comes across as 9.11 ohms. So next we are told to design this number by limiting the dV/dt. IRR we calculated using the typical value because the question is telling us that using the typical values of QRR and TRR. So the typical values of QRR and TRR are 115 nanoseconds and 505 nanocoulomb respectively. So we'll use these values to find IRR. Okay, so I hope that's clear. And here we'll use the same value. So this is 8.78 that we got from the typical value. So the voltage rating of CS will be basically the voltage spike that comes across CS. So that will be the voltage rating of CS. So for example, here it is 50 volt is the E value, and we are limiting it to twice E, which is 100 volt. So the voltage rating has to be more than 100 volts. And the type of capacitance, so that depends on your uh, the value of the capacitance. If the value is less, then you may use ceramic capacitors, and if the value is less as well as the voltage rating is less, and otherwise you have to use some other kind of capacitors, film capacitors or even electrolytic. And the power rating of RS will actually depend on the power loss associated with RS. So uh, so I think so that can be also complicated based on if you want to find the I expression, the RMS value of that I expression, and then RMS square into the RS value here. So that will give us the power rating of I RS. Or you can also, I think you can simplify it as well using IRR square times RS, but that may not be accurate because IRR may not be the peak value or may not be the RMS value. But basically, you have to find the RMS value of the snubber current, and then based on that, the power loss in the snubber capacitor. So the next, we are asked to design the snubber by limiting the dV/dt. So the dV/dt we have to limit it to half of the dV/dt rating of what is given in the data sheet. And in this case, CS we are told to choose as 2 nanofarad. So first we have to find the basically the normalized value of dV/dt, which is dV/dt divided by uh, E into the natural frequency. So dV/dt we are told is half of the value in the data sheet. The value in the data sheet was 7 volts per nanosecond. So half of that is 3.5 volt per nanosecond. And again, you can just be careful and see what is the how the value in SI units. And then omega 0 is basically 1 by LP times CS, and CS is already given. So then we get basically this value, and then we can find the expression for dVdt average divided by E omega naught, which comes across in this case as 0.28 amperes. So this whole thing, if you see the unit, it will come across in amperes. So now the uh, based on these values, so we found the value of this expression dVdt average divided by E omega 0. So we will, so this point 0.5 is basically the question previously said told us. So here we are told the dVdt limit is half of the dVdt limit given in the data sheet. So the data sheet tells us the dVdt limit is 7 volts per nanosecond. So we use half of that. So that is where the zero point 0.5 comes in. So just like we saw in the previous case, you use the value and you in the graph and you find chi naught and zeta naught. So it may not actually, so in the question it is just given as a uh, some value of zeta naught and chi naught. It may not be actually what is found from the graph, but the the actual method is once you find this value, you go to the graph and then you find the value of chi naught and zeta naught. So here we are given chi as 0.9 and zeta as 0.15. So we can find the value of RS using this expression, and we have to substitute the value of zeta here as 0.15. LP is 8 nanohenry, and CS we are already given as 2 nanohenry. So we will get RS as 0.6 ohms. So you can see the difference between the values of the RC snubber for uh, peak voltage limiting and dVdt. So in the first case, C was some 60 picofarad and R was around 9 ohm. In the second case, C is 2 nanofarad, which is like much higher, and R then decreases to 0.6 ohm. So based on your different requirements, the values of RC snubber will be different. Now the third design is the compromise design. So so basically we have to find the value of this term dVdt average times LP into IRR divided by E square. And once we find the value of this expression, so it is comes around 0.098, and since in the question we are told to round everything to 2 decimal places, so it will come across as 0.1. And then again we use the graph. So the question tells us then the corresponding values of chi and zeta will be 0.1 and 0.9. So then we can use the expressions to find CS. Uh, Again, it will come across as 20 around 25 nano, 24.67 nanofarad, and RS will come as 1 ohm, around 1 ohm. So these were basically the questions about the RC snubber. So next we have some other questions. So from the data sheet, the typical turn off time of the MOSFET we have to find in nanoseconds. So if you see in the data sheet, this is how the uh, times are defined basically. So there is a delay time. So that is basically uh, the delay when VGS uh, go, reduces, and then when the VDS starts to increase, and then there is a time between the VDS 10% to 90% as it increases. So that is TF. So the sum of these two is basically your turn off time. And if you find this from the data sheet, it will be as 39 plus 35 uh, nanoseconds, which is 74 nanoseconds. And we are told to give the typical turn off times. So the next question is about bootstrapping. So what are the disadvantages of bootstrapping? And you have four options: low noise immunity, whether it can or cannot drive high side switch, applicable only where gate driver requires low power, and can drive MOSFETs but not IGBTs. So can anybody guess what is the answer? So the answer can be more than one of these options. So can you guys guess which ones are the answer? So you can write in the chat what you think is the answer to this question. So we saw basically that uh, the bootstrapping method, it does not have isolation. So that is why it actually leads to low noise immunity. As for the second point, the whole benefit of using bootstrapping is to drive the high side switch using without the isolated DC-DC converter. So bootstrapping method can drive high side switch. So this one is not true. The third one, it is applicable only where gate driver requires low power, and so this is what we saw. Because of the capacitance value, it is limited to driving low power. And finally, in terms of MOSFET and IGBTs, it is not really relevant. It can be used for both MOSFETs and IGBTs. So B and C are not true. Only A and C are true. So the answers are basically A and point C. Next, we have the question that the main role of snubbers in power electronics converter is to, and we have different options, whether to reduce the spikes during turn on and turn off, to reduce the conduction losses, to reduce the inductor size, change the voltage gain of the converter. So what do you think is the answer? Yes, so the snubber cannot change the conduction losses. It cannot really change the inductor size, and the voltage gain is usually not affected by the snubber or the RC snubber that we saw. So the answer to this one is only that it is used to reduce the spikes during turn on and turn off times. So these were all the problems that we had for today. So if you have any more questions, you can ask in the chat, or you can unmute and ask using the microphone. So any questions? So if there are no more questions, then uh, we can end the session. Those who want to leave, they can leave. I'll be here for some few more minutes, and if anybody has any question, they can ask. So there is a question about the RCD snubber. So the RCD will have a diode across the resistance, and that will just change the how the circuit will behave during uh, the charging of these snubber capacitance. And so that will just have a different uh, circuit during the charging. So it has some advantages and some disadvantages in terms of loss, etc. So that I have not covered in this summary, but you can refer to there are two more lectures in the course on that. So, but basically there are different types of snubbers, not only RC and RCD, but in terms of there are inductor based snubbers and all that. And so different snubbers will have different pros and cons. Another question is what happens to the excess energy that the components of an RC snubber absorb. So the the C value, the snubber capacitance will take the voltage, and that will lead to some uh, the energy in the snubber capacitance, and then some of it will get dissipated in the snubber resistor, and some of it will get dissipated in the device as well, because when the snubber gets discharged based on where the current flows, it will get dissipated in the resistor or the device. For snubbers, there's actually a lot of material on snubbers. One, I will, if you want more details of this analysis, you can use this paper. It will give the RC snubber analysis. Other than that, you can find different application notes or papers. So different papers will give their, some papers are optimizing the loss, some paper are optimizing the voltage spike, and some are using RC, some are using RCD, some are using it across one device, some are using it across the whole leg, half bridge leg. So based on what you require, you can find a relevant application note or a paper. But this paper will give the details as are mentioned in the course. So there's a question, is snubber mandatory or optional? So no, it is not mandatory. It depends on how. if the parasitics are affecting your converter so that the spike is too much, and in that case, if you want to limit the spike, then you can use the snubber. The other option is you can also increase the gate resistance, but that will create more loss, switching loss. So it depends on your requirement. If you have some device where the rating of the device is very high, but the operating voltage is less, so even if there is a spike, it will not create a problem, then you need not use a snubber. So it depends on the application and the requirements, but it is definitely not mandatory.
Sir, can I have ask one question?
Yes.
Sir, as assessments with the different questions, in the first one it is for 10 marks, in the second one is for 20, third one is again 15, 10. As questions are with the different marks, how are you going to consolidate?
Uh, so as I mentioned, I think previously, I'm not really involved with the assignments and the exams. So I'm not. If you have any questions regarding that, you should ask in the portal. There is some the Google group. You can ask there because I am not really. I don't have information regarding that.
Hello, sir. So I have
Yes.
a doubt regarding the turn off and turn on switching characteristics of a MOSFET. So I want to ask that why always the first the current is rises during the turn on, and then the voltage drops.
Yeah. So that is basically depends on the device physics and how that happens. So there is no. So if you want to go, you have to see the device physics and how the charge builds up and all those things. So there will be some equations regarding that. And so that is like beyond the scope of this course.
Okay, sir.
So it basically depends when the threshold voltage gets crossed, how the what is the expression for the current, and and then after that the voltage will change. But it's not really important for you to know uh, why these things happen. Just you have to remember uh, this is how it happens, and then you can use this understanding to basically understand the loss process, and then the loss you can uh, the loss you can change based on the snubbers, the gate resistance on all these things. But how actually the switching takes place, that depends on the device physics, and that is like semiconductor stuff. So if there are no more questions, then we can uh, about the pulse transformer. So right now I don't have those waveforms, but if you see in the course lecture, those are given. It is given for different duty ratios and all, uh, how it will change based on the duty ratio and how uh, if we reduce. if we add the DC blocking capacitor, what will happen, and then why do we use the restore, uh, basically the restore circuit. So I don't have the waveforms here, but you can see that in the course, as well as there is a document from TI which is about fundamentals of gate driving circuits for MOSFET and IGBT. So if you just search in Google fundamentals of gate drivers, MOSFET, IGBT, TI, Texas Instruments, you will get a document, and they have one section on pulse transformer based gate drivers. Okay, so I hope this was useful. So I'll see you again in the next week for week 5. Thank you all for joining.